Do the lab on gas laws in our laboratory. Here is a periodic table. I just want to mention this to start off with. These are our elemental gases, and we have our noble gases over here on the far right. And then the other ones that in the elemental forms are gases are H2, N2, O2, F2, and Cl2. Those are our diatomic gases. The noble gases are monoatomic gases. Here's just a list of common gases, and should mention that these are gases at 1 atmosphere and 25 degrees C. So under normal laboratory conditions, we would expect all of these to be gases. The ones we talked about that are elemental forms, as well as there's a good number of molecular gases such as carbon monoxide, carbon dioxide, methane, ammonia gas. Here are some characteristics of gases. Gases are compressible, so they can be, if we push on them, we can compress them down into a smaller volume. Gases are expandable. If we move and put them into a larger space, they will expand to fill the space. Gases have low densities compared to solids and liquids. Gases may be mixed in a fixed volume, so we can always mix 2 gases or 3 gases or 4 gases together. And gases exert constant pressure on the wall of their container, uniformly in all directions. What exactly is this gas pressure that we talk about? Well, if we think about the gas molecules as ping pong balls inside of a container, they're constantly in motion and they're constantly striking the surface of the container. They hit the surface of the container with some amount of force, and they exert that over the area of the container. And so force divided by area is what we define as pressure. Here's a zoomed in version of that. If we have a low pressure gas system here, the gas molecules are hitting each other and the gas and hitting the walls of the container relatively infrequently. However, if we have a higher pressure of the same gas, they're going to be striking each other, imparting force to each other, as well as striking the walls of the container more often. You're going to do a paper lab part on Boyle's law, and here's the setup that Boyle originally used. He set up this tube where he could trap some amount of gas over here with a stopper, and then he could increase the amount of gas by adding mercury to this right side of the so-called J tube. So he saw that the added height of the mercury was inversely proportional to the volume that he saw here. And so as you increase this column of mercury, the gas gets squeezed down into a smaller volume, and it's proportionate to each other. So if he doubles the amount of mercury that's in the column here, the volume would decrease by half. It's interesting if you take, and this is another setup where one could do this, if you take this and you squeeze this gas down into smaller volumes, you see that as you decrease the volume, the pressure goes up, or as you increase the volume, the pressure goes down, and you get this sort of parabolic curve that you have here. It isn't, in fact, until you plot either 1 over pressure versus the volume, or the pressure versus 1 over the volume, that you see that it has an inverse relationship. You get a perfect straight line if you plot the inverse of pressure versus volume, or the inverse of volume versus pressure. The volume of the gas is inversely proportional to the pressure at constant temperature and constant number of moles. So we have to control temperature to make sure that it stays the same, and we don't either add any gas or take any away. When we do this, that we eventually arrive at Boyle's law, which is P1 times V1 is equal to P2 times V2. This is a nice setup just to look at Boyle's law at 2 different points. You'll notice that the temperature is the same before and after. The volume, however, we twist this handle and we take the volume of the gas down from 4 liters to 2 liters. So the volume decreased by half, and it went from 4 to 2, and the pressure went from 1 to 2. And so this is a 1-point proof of Boyle's law. If we look at pressure times volume, so it is 4 times 1, which is 4 liters times atmospheres. And then over here, it's 2 liters times 2 atmospheres, which is, in these weird units, 4 liters times atmospheres. So P1 V1 is equal to P2 V2 at any point. Here's a molecular interpretation of Boyle's law. We're now thinking about what's going on with the particles, and we're exerting pressure by adding a weight to this piston. So on the left-hand side here, we have a 1 kilogram weight. On the right-hand side, we have a 2 kilogram weight. So we increase the pressure. We double the pressure by doubling the weight that's on top. What does that do? It pushes the gas down from a volume of 1 liter down to a volume of half a liter. And again, so if we multiply 1 atmosphere times 1 liter, we would get 1 here. And then over here, we get 2 times a half. 2 times a half is also 1. And so we still have P1 V1 is equal to P2 times V2. Okay, we're also today going to look at the Gay-Lussac's law. And this relates pressure and temperature. If we start over here at the high temperature side, we have high temperature, which we're causing by heating the glass with this water bath. And then if we slowly first turn the hot plate down to about half as the temperature, as we give it some time to cool down, you'll notice the pressure drops. And then if we let this cool all the way down to regular room temperature, the pressure drops even further. And so we see that the temperature and the pressure are directly related to one another. And here again, we're controlling volume. So the flask is the same size. We're not modifying the size of the flask, and we're not changing in, so we're not allowing any gas to escape, and we're not adding any gas. So at constant V and constant N, we get this relationship, which is now called either Amundsen's law or the Gay-Lussac law, which relates temperature and pressure. Shows they are directly related. What you're going to do today is you can use this to figure out what absolute zero is on the Kelvin scale. And if we look at this particular set of experiments was done with carbon dioxide gas, and we plot 1, 2, 3, 4, 5, 6 points here, starting around 400 Kelvin. And we look at these different plots and obtain a linear fit, and we should get absolute zero if everything was done properly. I want to mention here that the lowest temperature we can in fact go with carbon dioxide is around 200 Kelvin, because below that temperature it liquefies, so we have to extrapolate down to absolute zero. But we can get a good number of points for a fit above the 200 Kelvin, and therefore we feel good about extrapolating our line down to 0 Kelvin. All right, your specific experimental setup that you're going to have today. Here's the setup. You want to have the ring stand. This is to prevent this beaker from tipping over. Okay, we have boiling water in here, so we do have a scalding hazard, and so we've put this around here to keep this all stable. We use our arm that we add on to our ring stand in order to clamp down the flask, because this is full of a gas, and so it's going to want to float. We use this to force it down in there. And then finally, the temperature probe can just rest after we set this up down in the crease in this arm. And so your setup should look something like this today. You should notice that we want to be very careful to keep the tubing away from the surface of the hot plate, and to keep all of the wires away from the hot plate. So we don't want this wire to touch the hot plate. We want to be careful also that this wire down here doesn't touch the hot plate when it's warming. I want to point out exactly how the valve works on this setup. So what I have up here on the upper right, so when we have this orientation where the valve is in line, this is the open orientation of this valve. If we rotate this by 90 degrees, we get the closed orientation. And here's a front view of that. When it's along the valve, it's open. When it's perpendicular to the valve, then it is closed. Also, I want to point out for this lab, you are going to start the lab with heating the gas, and you're going to keep the valve open. It's a sort of a chemistry rule of thumb and law that we follow, is that you don't heat a closed system, because that closed system can explode if the pressure gets too high. Here, really what you would end up doing is most likely is popping this off. But we want to get you started following the rules in the right sort of way here. You don't want to heat a closed system. And so while you're doing the heating, this valve is going to remain open. When you get to the point where it is up to the temperature that you want it to be, you're going to close the valve, and then the valve is going to stay closed as you collect all of your low temperature data. So in lab today, I want to point out that the link that you'll need for the first half of the lab, which has to do with the gas simulation, is in Module 13. You want to open up Module 13 on your computer and go there to do that simulation. Complete the gas simulation packet before moving on to the wet lab part of this experiment. In the experiment, leave the gas valve open while heating the flask for reasons that we talked about. Again, open means it's a long, closed is perpendicular to how it flows. No wires or tubes should touch the hot plate surface. And then once you get to the point that you have it up to temperature, you're going to close the gas valve and you'll be cooling the flask. And you do not want to open that valve until you've run all the way through the temperatures, the low temperatures, because you don't want to have any gas come in and you don't want to have any gas go out. So in lab today, safety is going to be what I say every week. Everyone in the lab will wear goggles and a lab coat throughout the whole time in the lab room. You can take a break in the hallway if you need to take your goggles off. Goggles need to be worn over the eyes and not on foreheads or chins. For cleanup, all we're using is air and water. So the liquid, which is just water, can be rinsed down the drain. Make sure the gas pressure sensors are returned to the appropriate location that you found them. You can wash glassware if it's been dirtied in the process, and you can use a disinfectant wipe to wipe down the surfaces of your workstation.